Yeah, hello, my name is Juergen Goetz. I'm based at the Queensland Brain Institute of the University of Queensland in Brisbane. Today I'd like to talk about low-intensity ultrasound as it restores long-term potentiation memory in senescent mice through pleiotropic mechanisms, including NMDA receptor signaling. In my team, we use ultrasound using three fundamental treatment modalities. We use ultrasound in a scanning mode, which means that we treat the entire brain. And we use scanning ultrasound either on its own. We use scanning ultrasound with microbubbles to achieve blood-brain barrier opening. And we are also using scanning ultrasound with microbubbles and therapeutic agents, such as monoclonal antibodies, to deliver therapeutic agents. Over the years, we have been applying scanning ultrasound to Alzheimer's disease mouse models with an amyloid and tau pathology, but lately also to senescent mice. And by applying ultrasound, we basically are dealing with three fundamental properties of ultrasound. On the one hand, ultrasound is a radiation force. On the other hand, it exerts cavitation, especially when combined with microbubbles, and we believe that for the conditions we are using, heat can be neglected. Now let me now move to senescent mice. So when we look at physiological aging, we find that aging is characterized by a series of hallmarks. These hallmarks overlap with Alzheimer's disease, or to be more precise, they are augmented in Alzheimer's disease. In the lab, we assess cognitive functions by using the active place avoidance test. This is a test where a mouse is being placed in a platform which rotates. There's a shock zone indicated in red. The shock zone rotates, and the mouse then has to use visual cues to avoid the shock zone. And the mouse is tested every day, and eventually it will learn to avoid the shock zone, so hence it will receive less shocks. Now, when we look at C57BL6 wild-type mice, a mouse strain routinely used in Alzheimer's research, also as a background strain for the conventional transgenic mouse models, we find that these mice have an average lifespan of approximately 24 to 26 months of age, and they reach senescence at around 18 months, which also means that at 12 and 18 months, their performance in the active place avoidance test is relatively normal. However, at 20 to 22 months, their performance starts to decline. There's also an electrophysiological way to assess memory, known as long-term potentiation. It's an electrophysiological correlate of memory, and again, this induction is possible at the ages of 12 and 18 months. However, at 20 to 22 months, mice are impaired. So we use scanning ultrasound in the scanning, as I said, we use ultrasound in a scanning mode. And we routinely use the TIP system, annual array system. We either use homemade microbubbles or DEFINITY microbubbles. We establish parameters which are safe and effective. And we visualize blood-brain barrier opening by either using Evans Blue or Cargos or MRI. And we have in earlier work applied this technology to wild-type mice, looking at safety aspects, published in 2016 and 2018. And now we have a new study where we applied this modality to senescent mice, to senescent wild-type mice. And as indicated in the study design, we have been using 6 weekly treatments. And we made the remarkable observation that, as I've said, at this age, it's not possible to induce long-term potentiation. However, when we induce long-term potentiation, after applying either scanning ultrasound on its own or with microbubbles, we are able to fully restore long-term potentiation. Interestingly, we can also restore spatial memory or improve spatial memory functions. So on the left, you see 4 groups. You see naive mice. So these are mice where we have emitted anesthesia. We have a sham-treated mice. That's our normal control, where we anesthetize the mice, apply microbubbles, but don't use ultrasound. We have SAS plus microbubbles and SAS only, which means ultrasound purely as a radiation force. And you see that the most pronounced effects we find when we use ultrasound on its own. Interestingly, we also find that there is a dose-dependent restoration of memory. On the right, you see we go from naive to sham to scanning ultrasound plus microbubbles. And then we have either 1 weekly treatment, what we call single, 3 weekly treatments, what we call triple, or with sus-only paradigm with these 6 routine weekly treatments. And you can appreciate that there is a dose-dependent restoration of memory. The question is, how is this being brought about? And we believe that there are multiple mechanisms at play. On the one hand, there's increased neurogenesis, and it's dramatically increased in the hippocampus, and I know this has been reported by others previously. What we also did is we subcellular fractionated the hippocampus, and then performed Western blot analysis, and we looked for receptors which have a role in long-term potentiation, in particular the NMDA receptor and its subunits, A and B. We also looked at ERK kinase and a 6 kinase, and we furthermore performed swath quantitative proteomics. What we found by doing the subcellular fractionations was that we find changes to NMDA receptor signaling, which are conducive with the induction of long-term potentiation. And likewise, by quantitative mass spectrometry, we find changes in the proteome, which again are indicative of improved neuronal signaling. Now, let me quickly jump to Alzheimer's disease. Having mentioned the NMDA receptor, we have shown in the past, focusing on Alzheimer's, 2 pathologies, the amyloid plaques and the tau tangles, that A-beta is upstream of tau. That's the so-called amyloid cascade hypothesis. But we have also shown that A-beta exerts its toxicity via tau. When you remove tau, A-beta is not toxic anymore. And importantly, A-beta exerts its toxicity via activation of the NMDA receptor. So there's an overactivation of the NMDA receptor. So coming back to physiological aging, there's a belief that in physiological aging, there's a hypos, an underfunction of the NMDA receptor. And we believe with scanning ultrasound, either with or without microbubbles, we can restore this hyperfunction, kind of rescue the cognitive deficits which come with physiological aging. So looking at sus only and sus plus microbubble paradigm, we believe both show improvements, both lead to a restoration of the induction of long-term potentiation. We find that both lead to neurogenesis. They lead to different degrees to a digestion of the extracellular matrix, but by and large, we believe that all these changes converge on neuronal activation via the NMDA receptor. The question is which cell types are involved. There's work from Justin Lee's lab, and there's also work from Michael Shapiro's lab. Justin Lee's lab would indicate that ultrasound activates astrocytes. There's a calcium influx and a glutamate release. Glutamate then activates the NMDA receptors, leading to long-term potentiation. That's our bit of work. That's basically nicely fitting together. There's work from Michael Shapiro's lab done in cell culture. His work would indicate that the restorative effects he observed in neurons, that they are independent of the NMDA receptor and independent of astrocytes. In other words, they are cell autonomous. So the question still is open which cell types are involved and what the actual mechanism is. So we are working on that. We have taken this insight now into sheep. So we have performed a lot of sheep experiments. And we have, in the meantime, obtained approval to use a custom-built device, which we call Ultrafira Pilot. We have registered a trial, and we are now conducting a phase 1 safety trial in Alzheimer's patients. I hope this adds to the body of work from many research groups that low-intensity ultrasound is a safe modality with a huge potential to treat brain disorders. With my last slide, I would like to acknowledge the many collaborators, the funding support we have received, my mechanistic team, and also the ultrasound team. Thank you.